You know, we do things all the time. We start a car, we send an email, we brew a cup of coffee. But have you ever really stopped to think about when you can perfectly undo something? Well, today we're going to unpack two of the most powerful theorems in all of mathematics that give us the answer to that exact question. When can you actually go backwards?
It sounds almost too simple, right? A function is basically just a recipe, a set of instructions. If it takes you from point A to point B, shouldn't there be a reverse recipe to get you right back where you started? Well, as we're about to find out, the answer is a really powerful and honestly fascinating sometimes.
So before we get the big answer, we really need to dig into why this is such a core problem in mathematics. This isn't just about retracing your steps. It's about a much deeper question. Does a single, unique path back even exist in the first place?
And for our guide on this journey, we're diving straight into Chapter 7 of Marsden and Hoffman's Elementary Classical Analysis. This chapter is all about two absolute game changers, the inverse and implicit function theorems. You can think of this book as our map for today's entire explainer.
Let's make this super concrete. Okay, look at a simple function, like y equals 2x plus 1. If I tell you y is 5, you know with absolute certainty that x had to be 2. Easy. The path back is crystal clear. But now, what about y equals x squared? If I tell you the answer is 4, where did you start? Was it 2 or was it negative 2? See the problem? You've lost information on the way, and you can't be 100% sure how to get back.
That whole issue, that ambiguity, that's the undoing problem in a nutshell. But believe it or not, it gets even trickier. What happens when you can't even pull the variables apart to begin with? When your path isn't a straightforward do this to x to get y, but it's more of a messy knot where x and y are all tangled up.
Just think about the equation for a circle. I mean, it perfectly describes this beautiful relationship between x and y. But just try to solve it for y. What do you get? You get two answers, right? Y equals plus times or minus the square root of 1 minus x squared. It's not one clean function. For a single x, you could be at two different y's. The variables are stuck together, defined implicitly by that one equation.
So this brings us to the big question. How do we solve this first problem? How do we know for sure when we can go backwards? Well, this is where the first hero of our story steps in, the inverse function theorem. This is the mathematical tool that gives us a clear green light or red light.
And you know what its secret weapon is? Calculus. It's the derivative. The derivative of a function at some point tells you its slope right at that spot, its instantaneous behavior. It's like pulling out a super-powered magnifying glass that lets you zoom in and see exactly what the function is doing in that tiny, tiny neighborhood.
And here is the absolute key. The inverse function theorem says that if the derivative at a point isn't 0, meaning the function isn't totally flat right there, then you have a guarantee. Now, why does flat matter? Well, think about it. If the graph is flat, then a bunch of different inputs nearby could all lead to the same output. But if it's not flat, if it's slanted, you're guaranteed that in a small area right around that point, a perfect inverse exists. You can find your way back, at least locally.
Okay, so that gives us a solid rule for the undoing problem. But what about that untangling problem? You know, the one we saw with the circle, where all the variables are mixed up in a big equation. Well, this is where our second hero makes its entrance.
Meet the implicit function theorem. This thing is pure magic. It looks at that messy circle equation and says, yep, I know you can't write one clean formula for the whole thing, but near most of the points on that circle, you can absolutely think of y as a function of x. It literally finds the function that was hiding inside that tangled up relationship all along.
And that, right there, is its superpower. It gives mathematicians, scientists, and engineers the confidence, the permission really, to treat these complicated, messy relationships as if they were simple, well-behaved functions, at least in the little area they're interested in. It's a license to find simplicity inside of all the complexity.
Now, these two theorems, they're not just clever party tricks. As we can see right in our source material, they're foundational power tools. They are the bedrock that a whole range of other, even more powerful ideas are built on.
Just look at how Chapter 7 is laid out. It starts with our two theorems, but then it uses them to build everything else. Things like solving differential equations, and this is a big one, a technique called Lagrange multipliers. These topics aren't just in the same chapter by accident. The later ones are completely dependent on the guarantees that our first two theorems give us. So what in the world are Lagrange multipliers? They are a brilliant, brilliant way to find the best possible outcome. Imagine you want to maximize your company's profit. That's your goal. But you're stuck with a fixed budget. That's your constraint, an implicit function, just like our circle. The logic from the implicit function theorem guarantees you can work with that budget constraint, And it lets you find the one single sweet spot where the slope of your profit function perfectly aligns with the slope of your budget. And that point of alignment? That is your optimal solution. It's incredible.
Okay, I know this can all seem a little abstract, but I promise you these mathematical guarantees matter. A lot. They are like the hidden scaffolding that holds up so much of our modern science and technology.
And this really gets to the core of why this is so important. Before a team of engineers goes and spends years and millions of dollars designing a control system for a new rocket, a mathematician can use these theorems to prove that a stable solution is even possible. Just knowing that an answer exists is often the most important step of all.
And their fingerprints are everywhere. Seriously, in physics, they're used to model if a system is stable or if it's going to fly apart. In economics, they prove that a price exists where supply equals demand. Engineering, control systems, computer graphics, mapping textures onto complex 3D models. Even in machine learning, these ideas are at the very heart of how we optimize algorithms.
So, I'll leave you with this to chew on. The next time you see a satellite holding a perfect orbit or an impossibly realistic special effect in a movie, just remember the invisible theorems working behind the scenes. What other amazing things in our world are only here because, long ago, a mathematician could prove that an answer was out there, just waiting to be found?